Good morning, everybody, and welcome to the CEIA Maths Tutorials online. And this morning we have Jerry Sweeney, who's going to take the Algebra 2 tutorial, Algebra 2, including the Cartesian form of complex numbers. Over to you, Jerry.
Thanks, Eamon. Good morning, everybody. So I'm going to follow on from what Paul did last week, Algebra 1. We will take a break at the end of Algebra, and we'll come back, go make a cup of coffee, whatever. And when we come back, we'll work on complex numbers. About 20-25% of you may not have come across complex numbers based on the poll. Don't worry, we will approach it fairly gently. So those of you that were here for the first day, will remember I gave an introductory talk and I spoke about this concept of the map of mathematics. And today we're going to deal with algebra. And algebra is dealing with missing data. So we're using a number without knowing its value, and therefore we give it a name, and we call that name a variable name. And Paul touched on this last week, but I think it's worth looking at it again. We have expressions, and an expression consists of a number of terms, and we can put two expressions into an equation, and a function is a particular type of equation. It's an equation, okay, that has a single value for one variable, for each value of the other variable. And in real life, these occur very commonly. So an example of a function, okay, would be the population of Ireland over time. So it would have increased up until around 1850, and then it would have decreased, and then it would have started to increase again. But at any time, there is only one value for the population of Ireland. So therefore, it's a function. And for the Leaving Certificate course, we are going to deal with a group of functions that are referred to as polynomial, and in particular quadratic and cubic. That's those with coefficients of squares and cubes are the ones that we're interested in. So if you have a function of degree 0, then that's a linear function. And if you graph it on a line, so what you have on the left-hand side is you have quadratic expressions, and if you graph those as functions, so if you say f of x is equal to ax squared plus bx plus c, you create a function. And if we plot f of x as y, then we get a graph. And if you have degree 0, you get a constant function. You get a horizontal line. So that would be like x is equal to 4, and it will draw as a single horizontal line. Linear functions are degree 1, so they come in as a straight line, but a straight line with a slope. So for example, y is equal to x, it goes through the origin and goes at 45 degrees. And we then, if you take it to quadratic functions of degree 2, then you get a parabola. If you go to degree 3, you get a cubic function. and that means that the coefficient of x is a 3. And what you will notice if you look at these functions when you graph them is that every time you add a degree, you increase the degree of the function, you add another curve to the another twist to the curve. And what you will notice is that functions which are of even degree will, on both left and right, will on the left side of the graph and the right hand side of the graph, okay, will go in the same direction. So if we take this, let me just get a pen, and if we take this function here, this quadratic, you can see, okay, that both sides are going in the same direction. If you have an odd coefficient, then they will go in different directions. Now, because of the number of twists in the graph, a cubic expression is capable of crossing the graph in up to 3 places. Now, it is theoretically possible, okay, for those 3 places to coincide, but it must cross the graph in one place. So if you have a function with odd degree, then you know it crosses the x-axis in at least one place. And where a function crosses the x-axis, we call that a root. And we're going to spend a bit of time for the next 15 or 20 minutes talking about what a root is and what it means, okay, for something to have a root, and we're going to talk about how to find those roots. To help us to focus on the problem, I've selected this paper, question 2 on paper 1, 2018. And I think it's a very interesting question because it mixes up a couple of different ideas. So the first thing that it addresses, the first thing that it talks about is a geometric series. Now, a geometric series, so we're not talking about functions or expressions or anything like that yet. We're talking about a geometric series. So a geometric series is something where the ratio between any 2 terms is constant. And we spoke about having models in our head on the first day as well. So we need to be clear, okay, that the ratio between any 2 elements in a geometric series, any 2 adjacent elements is constant. So the ratio between the second and third is the same as the ratio between the 6th and 7th. And it describes the first 3 terms in a geometric series belong to x squared, 5x minus 8, and x plus 8, where x is a member of the rational numbers. Now, we want to use the fact that we have a common ratio. So this is a clue, okay, in case you couldn't remember what a geometric series was. So in the question, they tell you that there's a common ratio. So show that x cubed minus 17x squared plus 80x minus 64 is equal to 0. And the first thing we've got to do is to show that if 3 terms follow these constraints, then the constraints are represented by this function. This function, or to be more precise, they are represented by the function f of x equals x cubed minus 17x squared plus 80x minus 64, where f of x is equal to 0. And this is an interesting problem because it gets you thinking about what it means for something to have a root. And when something has a root, it means, okay, that it's equal to 0. It means that its value at that point is equal to 0. For a particular value of x, the function has a value of 0. So what we are asked to do then, as the second part of the question, okay, is that we are to take the function f of x, and we're to show that if we plug in the value of 1, okay, then we get it is a root. So we have to find that f of 1 is a root. And we have to find another value of x for which f of x is equal to 0. So it's asking us to find a second root. And the third part of the question is, in the case of one of the values of x, okay, from part B, you have to show that 1 generates a geometric series with a finite sum, and you have to find which one of them has a finite sum, and then you have to find the value of that finite sum. So this question mixes up two things. It mixes up series. So you've got geometric series. You've got to find the sum to infinity of the geometric series. But it introduces constraints. And those constraints are represented in the form of a function. And the constraint is met where the function is equal, gives a value of 0, where it crosses the x-axis, where y is equal to 0. Okay, so we will solve part A first of all. So we're given the three terms, the three first terms of the series, but we're given them in the form of an unknown value of x squared, sorry, of x. So we have to find out what the value of x is. We're told it's a geometric series, so we know that the ratio of the first two terms is the same as the ratio of the second two terms. So we can take the second term divided by the first term and the third term divided by the second term, and we can create inequality out of those. They must be the same. And we do some simplification on that. We take the 5x minus 8 from the right-hand side, where it's under the line, and multiply it on the other side, and we get 5x minus 8 squared. And we bring the x squared from under the line on the left-hand side to the right-hand side, and we end up with this. By rearranging the terms, we have solved the first part of the question. All you needed to do to understand this was to understand that the ratio of the first and second term in a geometric series was the same as the ratio of the second and third term. What I'm really interested in this question is understanding, is for people to get an understanding of what we're doing with this constraint. So we were given the values of the first three terms in terms of x. That's a constraint, and we're given the value of and we can turn that constraint into a function, and where the function is equal to 0, we have where the constraint is met. So in part 2, we have to show that f of 1 is equal to 0. You can say, if you're looking at it from a plotting perspective, that y is equal to 0. And it's it's very easy to do that. You simply plug in 1 everywhere where you have x. And f of 1 is equal to x cubed, which is 1 cubed minus 17 times 1 squared, plus 80 times 1 minus 64. 1 cubed and 1 squared is 1. So you've got plus 1 minus 17 plus 80 minus 64. And when you add those, you get 0. And what we've now done is we've proven that x minus 1 is a factor. Now, this class would benefit from being interactive, and it isn't interactive. We're separated out, but you guys can ask questions. So what I'm going to do is I would love to get questions around asking me, okay, what exactly is happening? I know that you know how to prove that f of 1 is equal to 0, but do you understand where this function came from? And do you understand how we created that, and where this is equal to 0? It is a constraint on the problem. Okay. So what we now need to do is to find another value of x for which f of x is equal to 0. We know that x minus 1 is a factor because 1 is a solution, is a root. So therefore x minus 1 is a factor. So what we can do is we can put in x minus 1 and in place of x, and now we're looking, okay, for the other terms. If x is equal to 1, then x minus 1, okay, goes away, and it becomes 0. It becomes 1, and we end up with x squared minus 16x plus 64 is equal to 0. We now have to get the roots of that, and the sophisticated way of doing that is to use minus b plus or minus the square root of b squared minus 4ac. But if a is 1, if the coefficient of x squared is 1, then we can work on the basis that the roots must add to b and must multiply to c. And it's obvious from that, okay, that x minus 8 and x minus 8 are the roots. So later we're going to plot that, and we're going to have a look at that graph. That graph, even though it's of degree 3, it only has 3 roots, but 2 of them coincide. So it doesn't cut the x-axis in 3 places. It cuts the x-axis in 2 places. But we still describe it as having 3 roots, but 2 of them are the same. So we have established that we have we 2 roots or 3 roots? We're going to say, well, we have 2 values. Okay, so the constraint is solved when x has a value of 1 or x has a value of 8. And what we can do then is we can start looking at the geometric series as for x equals 1, and we have the first 3 terms from the definition earlier. So it's the first term is x squared, the second term is 5 times x minus 8, and the next one is x plus 8. And the first 3 terms in the series come in at 1, minus 3, 9, and we know the ratio must continue to be the same, so the ratio is minus 3. So the next term after 9 will be 3 multiplied by minus 3, which is minus 27. And the ratio, if the modulus of the ratio is greater than 1, then that does not have, it doesn't have a sum to infinity. it doesn't have a finite sum to infinity. Okay, so that is not the one that we're looking for. So let's test x equals 8. And x squared in this case is 8 squared, 64. And the next term is 5 times x minus 8, which is 40 minus 8, which is 32. And the next term is x plus 8, which is 16. So in this case, the ratio in the geometric series is a half. So it takes 64 divided by 2 is 32, divided by 2 is 16. And the next one is 8, and so on. So we can see there, okay, that a is equal to 64. A is the first term, and the ratio is equal to half. Each term is half the previous term. And the sum to infinity, when you're doing series and sequences, this will be discussed in more detail. I have to just mention it here because this problem covers both algebra and series and sequence. So the sum to infinity is the first term over 1 minus the ratio, and that is finite. And since it's 64 over a half, then the sum to infinity of the series when x is equal to 8 is equal to 128. Now, I'm going to pause there for a second, and what I'm actually hoping is that somebody might come up with some questions, or if somebody wants to make a comment and say, look, I understand it, move on, that's cool. But I think this is an interesting problem because it mixes up a couple of issues. And whereas you might see how to solve the 3 parts of the paper quite easily, it may not be obvious as to how, as to exactly why you're following those processes. So if anybody wants to pop up on chat there a question, I'm happy to talk a little bit more on it. Okay, so what we're going to do now is we're just going to have a little bit of fun, and there is an excellent program available on the internet. I think it's desmos.org. If you're on a computer and you can open a browser, I would ask you to do that. I'm actually going to see if I can show the slide deck and the browser at the same time, so I'm going to have to pick one. Give me a moment. Okay, so it's desmos.com. So what I want to do is I want to look at some graphing functions. And if we go and we plot the function y is equal to x, we get, I mentioned this one earlier, we get a straight line going through the origin. And what I can do is I'm going to try and plot x squared. And what we see here with x squared is we see a parabola, and the parabola crosses the x-axis in 2 places. Sorry, it crosses the x-axis in one place, or it meets the x-axis in one place. So its 2 roots are coincident. So what I would like you to do, please, is to open a browser with desmos.com and actually try some of these functions yourself, because what I'm going to do is I'm going to actually ask you to solve a problem visually. when we get to the end of this. So it's going to require you to have that screen open. So if we can play with this and see what happens if we go -2. And what's happened is the graph has been shifted down by 2. So what we're plotting here is f of x is equal to x squared minus 2. And f of x is plotted vertically. It's on the y-axis. So by subtracting 2 from the right-hand side of the function, if you want to call it that, okay, then we have moved it downwards. We now have 2 roots, and I think you can imagine that if we went +2, we would move it upwards. So what happens if we put in -x? So what happens when we put in -x is that we have shifted the graph a little bit to the right. And if we put in +x, okay, then we've shifted it a little bit to the left. This x squared plus x plus 2 doesn't have any roots. So if you were to apply your formula, and this is a kind of a sneak preview to what we will be doing after the break, if you were to apply your rule for solving this type of equation for finding the roots, then b squared minus 4ac, okay, would be a negative number, and you would be looking to find the square root of a negative number, and you would have been told that that was impossible. So I think actually it's possible for me to use multiple. So let me go x to the power of 3. So what we've done now is we have a cubic equation. So we have a quadratic equation in red, and we have a cubic equation in blue. And let's make our cubic equation a little more complex. Let's put in x squared. So we have x cubed minus x squared. And actually, let's before we get to that, I should have pointed out something. X cubed is a cubic equation, and because it's a cubic equation, it has 3 roots, but the roots all have the same value. And the root, okay, is x equal to 0. It crosses the x-axis at 0. So y is equal to 0 when x is equal to 0. I would really encourage you to experiment. What we've done now is we now have found, by making it x cubed minus x squared, we have a second root, or to put it more precisely, we have a second place where it's crossing the x-axis. So it's still crossing it at 0, but now it's crossing it at a half as well. And let's put in a third term. It's a cubic equation, so we're entitled to have an x. And now we now have 3 proper roots. On the graph, there's a little dot where there is a maximum and a minimum as well. But you will notice that there are 3 roots, and if you mouse over it, will give you the location of the 3 roots, the value of the 3 roots. So the first value, the x value, is the one that you're interested in because the y value is going to be 0 when it's a root. What I would like you to do, okay, just to finish off, let's put in a constant and see what happens. So what happens now is we've added +2, and this has shifted the cubic. It shifted the function up by 2. We now only have a single root. it crosses the x-axis at one point. And what I was saying earlier, okay, is that if the order of the function is odd, then it must cross the axis in at least one place. If it starts to the left as a negative and ends on the right as a positive, then it must cross the x-axis. The parabola that we have drawn, x squared plus x plus 2, parabolas don't necessarily have to cross the x-axis. They can cross the x-axis 0, once, or twice, or I suppose it's more accurate to say they are equal. Sorry, if the roots are equal, then they touch the x-axis. I want to show you something that will be important in a moment. It's something that I find intriguing and caused me some confusion. If we change the coefficient for the x squared term, we are in effect inverting the function. I'm going to come back to that because there's something important. We're going to do a little problem, okay, that requires you to understand that. What I want you to be aware of, though, is that if you think of the coefficients of the function, okay, as being a, b, and c, that's what you use for your minus b plus or minus the square root of b squared and so on. If the a term is positive, then the parabola is a U shape. It's a cup shape. And if the value is negative, then the parabola is a cap shape. It's an N shape. It's an upside down cup shape. And that's important to remember. That comes up in a remarkable number of problems to figure out, okay, whether it's U-shape or cup shape. And we're going to solve a problem that needs us to realize that in a minute. So I'm just going to go back. I see a comment here. To see if it's a question, I will address it. No, it's just a comment. Okay, cool. All right. So I would encourage you to use Desmos as you're doing these problems to plot the functions that you're working with. And what I'm going to ask you to do now is I'm going to ask you to plot the function that we worked on with the problem. And that function is x cubed minus 17x squared plus 80x minus 64. So I hope I remember that correctly, but that's the function that we solved our problem with. And if I got that right, then we should see 1 and 8 as being the roots. So let's have a look at what that looks like. So I'm going to delete the other two because my graph is getting a bit overdone. So we go x cubed minus 17x squared plus 80x minus 64. And we have now plotted the function, and we're going to just reduce our scale. And yay, we get our two roots, and one of them is at 1, 0. The y value is 0, therefore it is a root. It crosses the x-axis. And the other one, I bet you it's 8. So that means I've remembered the expression correctly, and we've generated a function based on f of x is equal to that expression, and we got our cubic function graph, and we've now displayed the value of the roots in that graph. Okay, I'm just going to, if you want to play with Desmos there for a second, I'm going to go back to my slide deck. And I want to talk about quadratic inequalities. So I'm going to assume that you can see my screen and you can also keep Desmos open. So what I want you to do is, I want you to plot on Desmos, I want you to plot x squared minus 2x minus 8. I want you to plot that as a function. And this is a problem where we're asked to know, to solve the inequality. So Paul brought this up last week. So an inequality is where you have a less than or equal to sign rather than an equal to. And we're asked to find out where is x squared minus 2x minus 8 less than or equal to 0. And if you plot x squared minus 2x minus 8 on your Desmos, what you will find is that it crosses the x-axis when, so it's a parabola because it's x squared. The a term is positive, therefore it's cup-shaped. And the roots are minus 2 and plus 4. You should be able to see that on Desmos now. We don't have to use the minus b plus or minus the square root of b squared formula to find the roots of this, because there's a little simple rule. If a is equal to 1, if the coefficient of the x squared term is equal to 1, then b is equal to r1 plus r2, and c is equal to r1 multiplied by r2. So the only way that you can get two numbers to add to minus 2 and multiply to minus 8 is to have one of them be minus 2 and the other be plus 4. So with a little bit of practice, you can deduce that the first root is minus 2 and the second root is plus 4. So there are two possible answers depending upon whether the parabola is a U or a hat. And I've told you the rule already. If the a coefficient is positive, then it's a cup. If the a coefficient is negative, then it's a hat. So we're looking for where it's less than or equal to 0. And what you will notice is that because it's a cup, then between minus 2 and plus 4, it's less than or equal to 0. If it was a hat, then if it was minus x squared, then the answer would be it's less than or equal to 0, below minus 2, and above and greater than 4. One of the things that confuses me a lot about inequalities, as distinct from equalities, as distinct from equal to signs, is that you have situations where you have to, so here we have an inequality. And it's very important to remember that with an inequality, you cannot multiply both sides by minus 1. If you do so, you have to change the direction of the inequality. So if you say that x squared minus 2x minus 8 is less than or equal to 0, if you decide to multiply that by minus 1, you get minus x squared plus 2x plus 8 is greater than or equal to 0. And if you have Desmos open, you can prove that to yourself by taking minus x squared plus 2x plus 8, and you will find that the graph inverts, and therefore the if you've inverted the inequality, then you get the same answer, but if you don't invert the inequality, you get a different answer. Okay, so this is all I wanted to cover from an algebra perspective, but I wanted to just go off the course a little bit and just talk to you about something that I found absolutely fascinating about algebra. I hope this is outside the Leaving Cert syllabus, but I hope you enjoy it. So let me talk to you about your brain for a second. Okay, so how does your brain work? And your brain consists of neurons. And a neuron has inputs. I'm not an expert on biology, but it looks to me like they're called dendrites. And it has outputs called axon terminals. And electrical signals go into your dendrites and come out of your axon terminals. And you have axons, which can be quite large. I believe they go down the length of your body from your brain to down through your spine. So the other end of the cable, okay, is quite far away. Now, in the 1950s, they began to recognize how neurons worked, and they started to realize that brains are made of neurons, and they appear to be made of nothing else other than neurons. So they started to develop the technology, or to think about the technology, to build artificial intelligence. And what they came up with initially, okay, it's what they came up with, and they were quite correct, okay, is they made an analogy for a neuron, and it's called a perceptron. And it's a mathematical model, and you can calculate, there's a very simple, and what's interesting is that it's a linear formula. So the output, what comes out of the axon terminals, okay, is equal to a weighting of what goes into X1 plus a weighting of what goes into X2 plus a weighting of what goes into X3. So your brain is it is made up of linear algebra. And when you learn stuff, what you are doing is you are changing the weightings, the W1, W2, and W3 of your linear algebra. And you're also creating new axon terminals to different parts of your brain. But that's all you're doing when you're learning. You are creating connections in your brain, and those create relatively slowly. And you are modifying the weightings of the function. The functions of the neuron in computer terms, it would be a perceptron. Now, even though they understood this functionally, we did not make a whole pile of progress on artificial intelligence until about a decade ago. And in fact, there was a kind of a 30-year hiatus where very little work happened in artificial intelligence. But companies like Google now are spearheading it. And what they're doing is they're taking perceptrons and they're putting them into neural networks. So each one of these circles represents a perceptron. And they can train the perceptron. So you can feed in this neural network here, okay, might be trained to be a classifier. So in the input layer, you would put in a photograph of something on LinkedIn or whatever, and you would then have a classifier which would determine whether it was a cat or not. And you would train the hidden layers. Obviously, you would have a lot of inputs because you would have one input for each pixel. And if you had a megapixel camera, then you would have a million pixels going in. But the output might be a single axon. It might be a single output layer. And that would tell you it's a cat or it's not a cat. And you have multiple layers in the middle. And what you do is you show it pictures of cats. And there is a mathematical algorithm for training the hidden layers. So what I think, I'm going to finish the first part of this lecture. I'm a little bit early on the first part, so we'll start early on the second part, and we'll focus on complex numbers. So I'm finishing a little early, but that's not a problem. I think the complex numbers merit a little bit extra time. So I'm going to finish on this thought. You are using linear algebra to understand algebra. Have a break, and I'll see you back here in maybe, Eamon, if we start about 11:05. Will that work? Will that be okay? Okay, welcome back. All right, so about a quarter of the people say they haven't come across imaginary or complex numbers before. So we're going to do this very gently. I like to start with my map of mathematics. So what we have here is we're going to be working on arithmetic and algebra, and we're going to be applying them to imaginary and complex numbers. So that's the purpose of this session. Coming up to the junior certificate, you might have had a clue that there was something amiss. When you were solving quadratic equations, you were given the formula minus b plus or minus the square root of b squared minus 4ac over 2a. And if the discriminant was negative, you were told it can't be solved. Well, we're going to solve it today. So it can, if you allow the square root of negative numbers, and it is from this issue of the square root of negative numbers that imaginary numbers and then complex numbers have been derived. So what has been happening historically is that the number types have been extended down through the centuries. So we have natural numbers, numbers that you count apples and cows in. By adding in 0, you get the whole numbers. By subtracting one number from another, you end up with negative numbers. And I would encourage you to, in your mind, okay, think of complex numbers as having a kind of a relationship with negative numbers. If you can imagine that somebody would have difficulty understanding the concept of minus 2 apples, but yet we have no difficulty understanding negative numbers. We use them every day, and we do find applications for them, like the concept of debt, for example. If you owe money to a bank, okay, then it's minus a negative number. Rational numbers come from dividing two integers, and irrational numbers are numbers which cannot be defined as a ratio. They're not rational. And irrationals and rationals together are called real numbers. So today we're going to talk about numbers that are made up of square roots of negative numbers. So all we need to work with those numbers is to create a new number, iota or I, and give it the property, okay, that iota squared is equal to minus 1. Or that the square root of minus 1 is equal to iota. And complex numbers are made by adding a real component to the imaginary component. So a complex number is a number with a real component and an imaginary component. This is a Venn diagram of the different number types. And you can see that the outer set of all of the number types are complex numbers. And the good news is that once you get the complex numbers, you're finished. Nobody has managed to create a number using an arithmetic operator that is not contained within complex numbers. And I want to point out a couple of facts here. The first one is that all numbers are complex numbers. So if you write down 1, you can say it's 1 plus 0i. So the natural numbers, whole numbers, integers, rationals, they can all be written as a complex number by going plus 0i. The second thing that I want to make absolutely clear is that a complex number is a single number. So even though you go -3 minus 4i or 2 plus I, those are the examples there. It's not two numbers, it's a single number. We will use the phrase two components, but it is a single number. So 2 plus I is a number in the same sense that 5 is a number. It's not two numbers. And I actually, in the name of this session is referred to as complex numbers using Cartesian form. And in many textbooks, it's described as that, but I personally have a problem with that because we tend to use Cartesian coordinates as two numbers, 4, 3. An Argand diagram is a diagram on which you display complex numbers, and I prefer to use the phrase Argand diagram. And we will have examples of Argand diagrams in a moment. So the inability to find roots of negative numbers causes problems, and we solve the problem by creating a symbol for the square root of -1. And all imaginary numbers can then be written as a real multiplier of iota, or the square root of -1. So for example, the square root of -3, you will remember from Ed's logs and indices and so on, okay, we can separate that out into the square root of 9 multiplied by the square root of -1, and the square root of 9 is 3. Therefore, we can represent the square root of -9 by 3 times I. You only need the square root of -1 in order to be able to represent all imaginary numbers as a real number multiplied by I. And complex numbers then have two components. They have a real and an imaginary part, but it is a single number. I'm going to stress that. It is not two numbers. This was a problem that was brought up in Project Maths in 2012, and it took a Venn diagram and a bit simpler than the one I had 2 slides ago, but it introduced a little complication, and that is that it created a new set, okay, capital G, to be the set of x plus yi, where x and y were a member of z, so they were integers, and I squared was defined as being -1. And the first part of the problem, okay, was there are 3 regions in the diagram that represent empty sets. One of these is shaded, and shade in the other 2. Now, I would find that problem very difficult to solve by just addressing it. It's very difficult to prove stuff, in the negative. Have I thought of everything? But what I noticed when I looked at this problem was there was a second part to the problem. And the second part of the problem, okay, was to put into the diagram these 6 numbers, put them where they should be. And by filling those in, if a section in the diagram, okay, had one of those numbers, okay, then you knew it wasn't it wasn't an empty set. So what we have to do now is we have to look, okay, at where those are filled in, and my next slide shows them filled in, but I don't want to just pop it up on the screen. I want to talk about it for a little while. Now, the important thing to remember is the set G has x and y as integers. They belong to the set Z. So if we take one of these numbers here, okay, so 4 plus 3i. So let me get my highlighter. If we take 4 plus 3i and we ask ourselves, where does 4 plus 3i go? Oops, I went on to the next slide. Okay, let me go back. So I don't want to cheat and show you the answers. 4 plus 3i. So 4 plus 3i, the X and Y are members of Z. And if you have any difficulty remembering what Z is, it's actually shown in the diagram here as being an integer. So what you do is you take the 4 plus 3i and you figure out where that goes. Okay. So, so the first thing is it's not an integer as such because it is definitely a complex number, but it is a but everything inside in G, okay, it contains X and Y as being integers. So 4 plus 3i goes in here, and it doesn't go in complex numbers per se because because the value of X and Y are both integer. Let's take the second one, okay, 1/2 plus 2i. In this case, X is not a member of Z. Therefore, 1/2 plus 2i, okay, will appear here. It is a complex number, but it is not a member of G. So let's move to the next slide where they're all filled in, and let's prove these to ourselves. So the square root of 2 is not complex, but it is a real number. 1/2 is rational. 7 is an integer, and I've just filled in 7 plus 0i there just for fun, just to show that something that is an integer, okay, can be written with an imaginary component where the coefficient is set to 0. What we notice after doing this, okay, is that there are 3 sets that, there are 3 sections of the diagram, okay, that represent empty sets. There are no numbers in them. And it's now very easy, okay, to shade in the 2 remaining sets, ones where we don't have numbers. So in fact, if you went ahead and did section 2 of the question, you would actually either prove that you were correct in section 1, or you would actually have answered section 1 for yourself. Okay. So we're going to get to a little bit of algebra in a minute, okay? But let's talk about arithmetic. So what we said is that a complex number is a number. It's a number. Therefore, we should be able to add them. We should be able to subtract them. We should be able to multiply them. We should be able to divide them. We should be able to do logs and indices and everything that we do with normal numbers. Okay, we should be able to do with complex numbers, and in fact, that is true. And one mathematician in particular, a guy called Riemann, 160 years ago, okay, devoted his life, okay, to doing everything that we do with normal math, okay, with complex numbers, and everything works as you would expect. There are no, mathematics is not broken. When you apply complex numbers, everything works perfectly. So what we're going to do, first of all, is we're going to take these 3 examples, A, B, and C, and we're going to add the first 2, and we're going to subtract. We're going to do subtraction with the third one. So the rule here, okay, is that for addition, we add the real components together, the real parts together, and we add the imaginary parts together. And the technique then becomes trivial. So 3 plus 2 is 5, and 5 minus 3 is 2. So we get so the real parts are added. 3 plus 2 is 5, and the imaginary parts are added. Admittedly, adding a minus number is the same as subtracting, so we get a plus 2. If we go 3 plus 5i plus 6, then adding the real parts, 3 plus 6 is 9, and the 5i remains unchanged. Let's do some subtraction, and we've kind of almost done subtraction already because we had a negative number above on top. So this time, okay, 7i minus 4 plus 5i. The minus 4 remains as minus 4, and because we're multiplying the 4 by minus, and we're multiplying we're multiplying the plus 5 by minus, which makes it minus 5. So 7 minus 5 plus 7 minus 5 comes out at plus 2. So addition, if we follow that rule, is trivial, and mathematicians have worked out, okay, that this works in all cases and doesn't cause any problems or confusion with arithmetic. Multiplication is straightforward, provided that you remember that I squared is equal to minus 1. So what we're going to do is we're going to simplify these. They're not expressions because there's no variable in them. I is not a variable. So these are just these are just numbers that need to be multiplied together. Okay, so what we have here, okay, is 3 multiplied by 2 plus 4i. So 2 plus 4i is a number, and 3 is a number, and we multiply across, and we remember that I squared is equal to minus 1. The first case is pretty straightforward. 3 multiplied by 2 is 6. And 3 multiplied by 4i is 12i. So that's straightforward enough. In the second example, we will multiply a complex number by an imaginary number. And again, it's straightforward, except this time, okay, 5 multiplied by I comes out at 5i. So this is where this term ends up after we do the simplification. The bit that I'm really interested in, though, is the 3i multiplied by the I. So 3i multiplied by I will give us 3i squared. And I squared is equal to minus 1. Therefore, 3i squared is equal to minus 3i. And what's interesting here, okay, is that by multiplying by I, the real part has become imaginary, and the imaginary part has changed sign, but it has actually become real. And we will see that that represents something very interesting from a geometric perspective in a moment. We'll now do the more complicated version, okay, which is we're going to multiply a complex number by a complex number. And this is the same, I can't remember what it's called, where you do a full multiplication, okay, with 2 terms. There's a 4-letter acronym for it, I just can't remember it. So 2 multiplied by 3. So you do the first term by the first term, you do the first term by the second term, you do the second term by the first term, and the second term by the second term. So we expect to have 4 terms: 2 by 3, 7i by 3, 2 by 4i, and minus 7i by 4i. Am I right in remembering this is called FOIL? I can't remember what FOIL stands for, but I just popped into my head that I think it's called FOIL. Okay, so we multiply these out, and the first one is the first term is a real number. This one is an imaginary, and this one is an imaginary, and the third one is 7i multiplied by 4i, which is 24. 4 sevens is 28 multiplied by I squared, so that's minus 28, but there's a minus sign in front of it already. It's a minus 28, and therefore it becomes plus 28. We bring the 8i and the minus 21i together, and we get minus 13i. The 28 and the 6 simplify out, and we get 34 minus 13i. So it is FOIL multiplication, but remember, I is not a variable. We are multiplying two numbers. There is no variable. I is a constant. Now, the complex conjugate of a complex number is obtained by changing the sign of the imaginary part. So if we have a complex number, a plus bi, then its complex conjugate, which is written as z bar or written as any x bar, y bar, or whatever, z is usually used for complex numbers, is defined as z bar is equal to a minus bi. And something interesting about if you multiply a complex number by its own complex conjugate, okay, then you get a real number, which is a squared plus b squared. Because a multiplied by a gives you a squared. B multiplied by minus b multiplied by I squared gives you plus b squared, and the two middle terms in the FOIL cancel out. So multiplying a complex number by its complex conjugate gives you a 0. I might try try to work that out there. Okay, so just see if I can do this. So that's equal to a squared plus a b. Sorry about the writing. I'm doing this with plus abi minus abi. Minus b times, sorry, yeah, minus b squared, I squared. So appalling writing, but you get it. These two cancel out, and the minus and the I squared cancel out. So we end up with a squared minus, sorry, the minus and the I squared cancel out. So we end up with a squared plus b squared. So we're going to use that to help us with division. We're going to use that trick in order to do division. So the complex conjugate, okay, so we're going to simplify these expressions. We're doing division. So 3 over 1 plus I. What we can do is we can multiply above and below, okay, by 1 minus I. And we know that 1 plus I and 1 minus I will give us a real. So that means that what will be under the line then will be a real number. So let's do the multiplication. So above the line, so we're multiplying above and below by 1 minus I. Above the line, I'm going to get a different highlighter. So above the line, we get 3 times 1 minus I. And below the line, we get 1 plus I multiplied by 1 minus I. 1 plus I multiplied by 1 minus I gives us a squared plus b squared, which is 1 plus 1, which is 2. And above the line, okay, we do simple multiplication out and we get 3 minus 3i. We can then separate that into a real and an imaginary part, and we end up with 3 over 2 minus 3 over 2 times I. It is normal when you finish doing a piece of arithmetic on complex and imaginary numbers, that on complex numbers you separate them out into a real and imaginary number in order to finish your calculation. You present it as a real and an imaginary component. Your answer has those two components. In the stage before it, they're not separated out. So the second one that we want to do is 4 plus 7i divided by 2 plus 5i. we multiply above and below by the complex conjugate, 2 minus 5i above and 2 minus 5i below. The complex conjugate, where a is 2 and b is 5, multiplies out as 4 plus 25, which is 29. So we have 29 below the line. We do our FOIL multiplication on top. And I'm not going to do it out longhand, but we end up with 43 minus 6i. And again, we separate out the real and the imaginary part. And we end up with 43 over 29 being the real and 6 over 29 being the imaginary. Now, this is what we've done now is we've done addition, subtraction, multiplication, and division. And you can do your logs and your indices. These are just numbers, but this is all that we're going to cover on this session. And it's all that you're going to meet on the Leaving Cert. But the key takeaway from this is that complex numbers are numbers. And the regular arithmetic that you do every day, you can do with complex numbers. So we're going to move from arithmetic onto algebra. And we're going to introduce traditionally, we use x, okay, as a variable name. When we're working with complex numbers, we tend to use the letter z. So we're looking to solve the following equation. And this is like something you might get in the Leaving Cert, okay, solve the following equation for the complex number z. 1 plus 2i times z is equal to 2 plus 5i. So this, if you were thinking in terms of real numbers, this would be a times x is equal to b. That's all it would be. A times x is equal to b, where a is 1 plus 2i and b is equal to 2 plus 5. So what you do is z is equal to b over a. If these were normal numbers, that would be very obvious to you. To do division in complex numbers, you use the trick with the complex conjugate. You multiply above and below by the complex conjugate of the denominator. And the complex conjugate of 1 plus 2i, if you multiply 1 plus 2i by its complex conjugate, you get 1 plus 4, which is 5. If you FOIL out the top part, I'm not going to do that. That's something that you will be familiar with doing ordinary algebra. And that will come out okay at 12 plus I. And if you separate them out into the real and the imaginary part, you get 12 over 5 plus 1 over 5 times I. Now, we're going to go back to our Leaving Cert, our Junior Cert, and we're going to allow b squared minus 4ac, the determinant. We're going to allow it to be negative. So let's plug in a, b, and c into our formula for solving a quadratic, for finding the roots of a quadratic. And we get 2 plus or minus the square root of minus 4 over 2. And we're going to use the definition of minus 1 as being the definition of I being equal to the square root of minus 1. And we can take minus the square root of minus 4 and represent it as the square root of 4 multiplied by the square root of minus 1, which is 2 times I. So therefore, our answer is equal to 2 plus 2i over 2. We're just replacing the square root of minus 4. We're just replacing the square root of minus 4 here. We just replace that with 2i. And we've calculated that just overhead. We can separate that out into the real and imaginary, and we get 2 over 2 plus 2 over 2 times I, which is 1 plus, sorry, I forgot about the plus or minus, and that gives you x is equal to 1 plus or minus I. So therefore, there are two solutions, 1 plus I and 1 minus I. If you plot if you go back to our graphing software from earlier, and you plot x squared minus 2x plus 2, you will find that it does not cross the x-axis and therefore has no real roots. It does, however, have imaginary roots. And we're going to talk in a minute, okay, about what that actually means. What is interesting to note, actually, let me just go back to the previous one. If you look there, okay, we have two solutions, x plus I, 1 plus I and 1 minus I are the two solutions, okay, to that quadratic equation. That extrapolates out into the complex conjugate root theorem that states, okay, that if a plus b I is a root, then a minus bi is also a root. And that can be very important to remember. Oftentimes, okay, in leaving cert questions, I've seen this. Okay, you are either told or you can derive very easily one of the roots, and if it's a complex root, then you can work on it immediately. Okay, that a minus bi is also a root. So if you get one complex root, you can immediately assume the second one. We discussed earlier, before the break, okay, that if the degree of a real polynomial is odd, it must cross the x-axis at least once. And this is true because of the complex conjugate rule in a way, okay? So if the order of the polynomial is odd, then when we graph it, it was easy to see, okay, it had to go from being a very negative number at one side of the graph to being a very positive number at the other side of the graph, and therefore it crossed the x-axis. If every complex root of a polynomial, okay, has its complex conjugate as a root also, and the number of roots is odd, then there must be one root which is real. Because if that root was odd, it would have its complex conjugate as a root as well, and then you would be back to an even number of roots. So 2016, paper 1, question 1. So minus 4 plus 3i is one root of the equation az squared plus bz plus c, where a, b, and c are elements of R, and I squared is equal to minus 1. Write the other root. Well, I think we just told you if it's minus 4 plus 3i is a root, then minus 4 minus 3i must be a root also. So that's a very easy question if you know the complex conjugate roots theorem. 1 plus I is a root of the equation z squared plus 2 plus I times z plus 3 minus I equals 0. Find the other root in the form m plus ni, where m and n are real numbers, and I squared is equal to minus 1. So here we solve for z, and we use our good friend, minus b plus or minus the square root of b squared minus 4ac. But this time we have a complex root. Sorry, let me correct that. We have a complex coefficients. So a is 1, that's a real coefficient, but b is minus 2 plus 1, which is a complex coefficient, and c is 3 minus I. So I beg your pardon, I said that wrong. b is minus 2 plus I, which is a complex coefficient, and 3 minus I is a complex coefficient as well. The C coefficient is 3 minus I, and that is also complex. But we can still use the same rules of arithmetic in order to calculate the roots of Z. And we just plug it into minus b plus or minus the square root of b squared minus 4ac. So everything you've learned in algebra to date and in arithmetic work perfectly well, okay, for complex numbers. You've just extended the number set, but the same things happen, the same things work with them. So we have the arithmetic here is quite straightforward. We just have to remember that the square root of minus 1 is equal to I, and the only complicated part of this is where we need to go back to where we need to take the square root of minus 9 and we convert that to 3i, and whenever there's a square root it's plus or minus, so we get our two roots, 1 plus 2i or 1 plus I, 1 minus 2i or 1 or so Z has a value of 1 plus 2i or 1 plus I. So it's interesting that your technique for finding the roots of polynomials works equally well when the coefficients of the quadratic equation are complex. What I would like to do is to suggest that you spend a little bit of time studying complex numbers to get a better intuition into what they are and how they work. If you go to this website, welshlabs.com, you can download a workbook on imaginary numbers, and it goes through imaginary numbers in great detail and allows you to solve a lot of problems, and it gives you the historical context for imaginary numbers as well. So I would strongly recommend taking a weekend or maybe 2 or 3 nights, downloading this book and working through the worked examples. There is a video associated with Welsh Labs as well, where they visualize the roots of complex numbers. And in the past, when I've given this lecture, I've actually played the video live. I'm not going to do that today. I'm going to let you do it yourself. But if you go to welshlabs.com and watch that video, I believe it's up on YouTube as well. But it helps you to visualize. So what you need to realize is that when you work when you work with real numbers and you plot a function, you have an x-axis and a y-axis, and the x-axis is a single dimension and the y-axis is a single dimension. If you have a function, so y is equal to an expression that contains complex coefficients, then you actually have a two-dimensional number that you are mapping, okay, to a one-dimensional number. If you have a function that allows complex numbers on both sides, then you're mapping 2 dimensions to 2 dimensions. And it's very hard for humans to see and understand this. What they do in Welsh Labs is they plot complex numbers in 3 dimensions, which is easy for you to see. And the graph you're looking at there, the drawing that you're looking at there, is a parabola drawn in 3 dimensions where the roots are complex. So I'm not going to go into it today. I found it really fascinating myself when I studied it. I am strongly recommending that you go to Welsh Labs, you download the PDF, you read the book, you do the questions in the book, and you watch the videos that they recommend you watch, which I believe are up on YouTube, but you can get the link from Welsh Labs. Absolutely fantastic, and it will improve your understanding of complex numbers no end. Okay, now what we are going to do for the rest of the course, for the rest of today's session, is we're going to work with complex numbers on what's called an Argand diagram. And I'm going to go back and remind you, okay, that I have a problem with referring to complex numbers on the Cartesian plane because I believe the Cartesian plane represents pairs of numbers, whereas complex numbers are not pairs of numbers. It's a single number with 2 parts. So it's a single number. So an Argand diagram is not like a Cartesian plane. You don't represent it as brackets A comma B, you go A plus B. And the A plus B that's drawn here is a single number. And an example would be 3 plus 2i. So if we are to take, when you went to national school, okay, you were taught about the number line, and it was single dimensional. And what happened as we added, if you go back to the sets, the set theory where we added new number types, what we were doing was we were extending the number line. We started off with the, the integers and then we added the rationals, and then we added the irrationals and whatever. What we've now done in order to be able to cope with complex numbers is we have moved the number line into being the number plane. So we now have a number line which is 2-dimensional, and the number line is now 2-dimensional. And I'll talk in a moment, okay, for a little bit about it becoming more than 2-dimensional. But the number line that you learned about when you were in 4th class became 2-dimensional when you started talking about imaginary and complex numbers. Imaginary numbers are numbers which are on the vertical axis of an Argand diagram. Real numbers, which are ones that you have been dealing with up to now, are on the horizontal line. And complex numbers consist of a real and imaginary part, and they exist in the rest of the Argand plane or the Argand diagram. So in summary, the complex plane replaces the number line. So we're no longer dealing with a number line, we're dealing with a complex plane, a plane that contains complex numbers, of which the real numbers are a subset. We are going to redo our addition, subtraction, multiplication, and division using the geometry of the Argand diagram. So I don't know if we did this exact one, but earlier, okay, we added 2 numbers, and we added the real and we added the imaginary parts. So if we take 5 plus 4, and sorry, I beg your pardon, that's the answer. If we take 4 plus I, 4 plus 1i, and 1 plus 3i, we add the real and we add the imaginary parts, and we get 5 plus 4i. And this is the same as vector addition. You can draw one number as an arrow, you can draw the second number as an arrow, you can move the second number to the end of the first number, and the addition result is the distance, okay, from the start of the first arrow to the second arrow. So this is a visual way of representing Argand diagrams. a visual way of representing the addition of complex numbers on an Argand diagram. Before I go on to multiplication, subtraction is exactly the same, except the arrow goes in the other direction. You just flip the arrow. So addition is the same as subtraction. So if you wanted to subtract 1 plus 3i, it's the same as adding -1 minus 3i, and you're just putting the arrows together again. So I'm not going to explicitly do the subtraction one, but the idea is the same. Multiplication is really, really interesting for complex numbers. And I'm going to give you a little aside here just to convince you that multiplication of imaginary numbers or complex numbers is important. Okay, I'm sure every one of you has gone to Google Earth, and you've spin up Google Earth and you see this globe, and then you can catch the globe and you can pull it and it rotates. That is complex number multiplication. It uses three-dimensional complex numbers, okay, that are called Hamiltonians, which I will mention a little later on, but don't worry about it, they're not on the leaving cert. But what I'm saying to you is that multiplication turns out to be a rotation. And in my opinion, this is an amazing outcome. So what we did earlier was we took two complex numbers and we multiplied them out using that FOIL technique, and we ended up with a new complex number. What is fascinating here is that when we go to represent that geometrically, it turns out that what we do is we add the angles of the two complex numbers. So we add the angle on the Argand diagram of one complex number. So if the first complex number is A, that would be located here, then its angle is the angle A. And the second complex number, which is B, which is located here on the Argand diagram, its angle, the angle B, is here. And what is absolutely amazing is that when you multiply them together, A multiplied by B, you get a new complex number. And the angle of the new complex number is equal to the angle of A plus the angle B. And the length of the new complex number is equal to the length of A multiplied by the length of B. So if you were to measure the length of this, that would become a real number. So the length of A would become a real number. It's not where it is in the Argand diagram, it's its length. And if you take the length of A and you multiply it by the length of B, then you get the length of C. Let's go back and think about this for a second. Let's go back to the number line, okay? On the standard number line, if you multiply two numbers A by B, the angle of A and the angle of B are both 0. Therefore, if you add the number 0, the angle 0 to the angle 0, you get an angle 0. So therefore, you would expect that multiplying two numbers on the number line you're used to would yield a number on the number line. And that is what happens. So let's do an example. We will multiply two numbers. 1 plus 2i will be multiplied by 2 plus I. And on this Argand diagram here, we have drawn the two numbers, and one is red and one is blue. And it turns out, okay, that the angle for one of them is 26.6 and the angle for the other is 63.4 degrees. And if you add the two of them together, okay, you get 90. So what we're actually doing here is we're multiplying two complex numbers that each have a real and an imaginary part. And we end up with a complex number, but it's an imaginary number only because there is no real part. You can FOIL that out if you want to there. It's 1 multiplied by 2, so you can see the four multiplications. And then you have 2i multiplied by 2 and I multiplied by 1. And then you have the 2i multiplied by I, which is 2i squared, which is 2 multiplied by minus 1, which is minus 2. And you end up with 5i. So the length of the two numbers, or the magnitudes, I suppose, of the two numbers are added together, and the magnitudes are multiplied together and the angles are added. And I think this is an absolutely amazing result. So I actually mentioned this, I forgot I had a slide on it, okay? So that rule works for real numbers. So if you take 3 and multiply by 3, okay, you multiply the length of the numbers, 3 multiplied by 3, and you add the angles. 0 plus 0 is equal to 0. Therefore, you stay on the number line. If you multiply negative numbers, then a negative number, this is interesting, a negative number has an angle of 180 degrees. A positive number has an angle of 0. So if you take a positive number and a negative number and you multiply them together using the same rule, okay, you add the angles. So 0 plus 180 is equal to 180. Therefore, multiplying a positive and a negative number yields a negative number. And a very interesting example then is if you take two negative numbers where the angle is minus 180. So you add 180 to 180, you get 360. So minus 3 multiplied by minus 3, okay, gives a positive number 9. And this is why multiplying 3 by 3 is the same as multiplying minus 3 by minus 3, because adding 0 and 0 gives you 0. Adding 180 and 0 gives you 180 degrees. Okay, so that's the information I wanted to cover on the on complex numbers. But before I finish up, I just want to talk to you about my own kind of experience and history with complex numbers. Okay, so I suppose whereas doing the Leaving Cert, I learned about complex numbers. I was not aware of any practical application whatsoever of complex numbers, and I would have found that extremely unsatisfying. So I suppose the world is divided into, or the technical world is divided into mathematicians, scientists, and engineers. And mathematicians study what we've been discussing. They would find it very interesting as to how the definition of the multiplication of two complex numbers, two negative real numbers, end up being a positive number. That can be described by the rotation concept of multiplication in complex numbers. That would be a mathematician's view on it. Scientists would be trying to find a view of the world that would, a model is my word for that, okay? A model of the world, okay, that would be capable of making predictions, and they would utilize mathematics as a tool. An engineer, and I would see myself as an engineer, is somebody that would want to use mathematics to achieve results. So when I went to college, I studied electrical engineering, and we were introduced very quickly, okay, to Euler's formula. And Euler's formula introduced I as a concept for dealing with waveforms. And I did electrical engineering, which involves communications and so on. Everything is waves. You've got power waves in electricity, you've got electromagnetic waves for light, you have signals, electromagnetic signals, okay, for sending radio waves to your mobile phone or to your Wi-Fi or whatever. And these could be described extremely well using complex capabilities. So we learned, okay, to work with Euler's formula, and a sine wave could be represented by e to the j omega t, or I omega t. Engineers use j instead of I, but that's neither here nor there. So I omega t, omega was the angular velocity and t was the time. And by having this very simple way of describing a wave, we could do a lot of very complex mathematics. At the time, it struck me as being a trick. I didn't understand why it worked, and I graduated with a degree in electrical engineering, able to manipulate the formulae, but not 100% accepting that it was anything other than a trick, a mathematical trick. Mathematicians, by the way, throughout the centuries have, well, not throughout the century, but through the last century, okay, have voted several times to say that Euler's identity is the most interesting and most beautiful piece of mathematics that there is, that e to the I pi is equal to -1, or e to the I pi plus 1 is equal to 0. So mathematicians really like this, this particular type of mathematics. So, but I came out feeling very, very unsatisfied by the whole area of complex numbers, and I felt, you know, as if it wasn't particularly. I felt it was a mathematical trick, but I couldn't have an intuition into why it worked. The other thing I learned in college quite a bit was the concept of Fourier transforms, or Fourier analysis, and that e to the j omega t is in there. Think of j and I as being the same. And this was talking about waves and spectrum of waves. And there is a mechanical insight into this, okay, which was really, really elegant. But it did give me a feeling, okay, that there was something really good going on here that I didn't fully understand. It was about 10 years ago when I started teaching complex numbers to my own kids that I went back and I found Welsh Labs and I started studying it. And I realized, you know, there's an inherent beauty here that if you accept it, it is it's really cool. And that's why I would I would ask you to follow that little Welsh Labs course. It will start to create that intuition for you. In college, I learned a little bit of quantum mechanics, but a couple of years ago, about 4 or 5 years ago, I went back and I started to study it again. And it turns out that whereas you could do everything in electrical engineering without complex numbers, it would be difficult, but you could do it. It turns out that in quantum mechanics, there are things that you need complex numbers in order to do. They don't work unless you have complex numbers. And we live in a universe which is multidimensional. And I have started to form the opinion that the reason why it's multidimensional is that the underlying number system is complex. We have right angles. We have the ability to walk around the corner. We have the ability, okay, we live in a universe where the Rubik's Cube is possible because of complex numbers. So I'm going to finish on a sentence, and the sentence is, please accept that complex numbers are numbers. Please accept that the world is based on complex numbers. How the world operates requires complex numbers to exist. I just want to try on one other little point, and that is the two most famous mathematicians in Ireland. I think George Boole would be number one, and he was responsible for inventing Boolean algebra, which is used in every computer system in the world. And the second most famous mathematician in Ireland, I believe, okay, was I think it's William Rowan Hamilton is his name, and he invented a branch of mathematics based on three-dimensional complex numbers, and it is those three-dimensional complex numbers that are used in game playing, in spinning the globe, in Google Earth, and in landing spacecraft on planets remote from Earth and so on. Anything that involves rotation or movement in 3 dimensions tends to be done with Hamiltonian. So what I'm saying to you is these are not a trick. The universe is based on complex numbers. And the more you study physics and the more you study the world around you, the more you realize that. Because the first session was short, I finished a little early, but I'll give you the rest of your day. Okay. So, Eamon, can I pass back to you there, please? And thank you very much.
Yes, thank you, Jerry, for a very, very interesting session on complex numbers and Algebra 2. All is left to do so is say thank you very much, Jerry, for a very interesting session, demystifying complex numbers and making it applicable to our everyday world. So for the students, then hopefully we'll see you next week for the trigonometry 1 and 2 tutorial. Okay, so bye for now.